In the previous lecture, we were trying to calculate the bit error rate when we transmit a binary signal, that is signal that has two levels which are logically denoted by +1 and -1, and their amplitudes could be, let's say, plus Vp volts and minus Vp volts. This signal is detected at the receiver, but in the middle some noise is added, some voltage noise, let's say, and then you make a decision on the sum of the input signal and the noise. The input signal has two values, plus Vp or minus Vp, but this noise, this has some Gaussian distribution, let's say, with zero mean. Okay, and then it's easy to calculate the bit error rate. The probability density function of this itself will be 1 over square root 2 pi times sigma, exponential of minus Vn square by 2 sigma square. Okay, this is with zero mean. So now the signal that appears here, right, that will have the same distribution shifted either by plus Vp if +1 is transmitted here, or minus Vp if -1 is transmitted. Is that okay? That's pretty clear, right? So the probability density function of Vn itself is like this. Okay. Now Vi plus Vn, if I call this, let's say, Vx, then if Vi is plus Vp, when Vi is plus Vp, the mean of the distribution shifts to Vp. Okay. When Vi is minus Vp, the mean of the distribution shifts to minus Vp. Okay. Now what is the error ratio? First you assume that the probability of sending a +1, that is probability of the input signal being plus Vp, and when you send Vp there is some probability of error that is given by this area here, right? When you send Vp, but because of addition of noise the input signal is negative. So how much is that? What is this area? What is that? So let me call this PVN of Vn. So that is the probability density function of Vn. So what is that area actually? So this is integral from minus infinity to minus Vp. Okay. So basically this area is essentially this area here, right? The area to the left of minus Vp. So minus infinity to minus Vp, whatever the density function you have. Okay. And then similarly, you could be sending a -1, but then it can cross over to the positive side with this probability. And how much is that? What is that? From Vp to infinity. Okay. Now this P of 1 and P of -1, it depends on the signal, but it's most common to assume that you have equally probable plus and -1 symbols. That's when you have maximum information also. Okay. You are equally likely to get either 0 or 1 or +1 or -1. So each of these becomes half, and then from the symmetry of this distribution you also know that these two integrals are the same. Okay. So the bit error rate is nothing but where this function is 1 over square root 2 pi sigma exponential minus Vn square by 2 sigma square. Okay. And this integral is given a name because it occurs so often in communication systems. This is called the Q function. Okay. And as you can see, it depends only on this Vn gets integrated out. So it has only two numbers here, Vp and sigma. Okay. It is a function of Vp divided by sigma. Okay. Vp is the symbol amplitude or half the symbol spacing, right? That is, what I mean is, you have the plus 1 symbol here, minus 1 symbol there. The distance between them is 2 times Vp and half of that is Vp. Okay. So that's what appears in the numerator, and what appears in the denominator is the standard deviation of noise that gets added. We are assuming, of course, a Gaussian distribution here. Okay. Is this fine? Any questions about this? So this Q function is just another name. I mean, we could always write it like this. It's just a more compact notation for the same thing. That's all. It's also worthwhile kind of remembering like some, so it depends on this Vp by sigma is like signal to noise ratio. Vp is the signal amplitude and sigma is the noise standard deviation, right? And as you expect, if the signal becomes larger or the noise becomes smaller, this bit error rate goes on reducing. Okay? And you may know this already. What is Q of 3? Do you know? It's these are all approximate values, approximately 10 to the minus 3. And you keep hearing things about 3 sigma quality and so on, right? I mean, if you are above 3 sigma, it means you are 1 in 1,000 type person. Okay? I mean, good or bad, it could be either way. So whatever you measure. Now, the kind of bit error rates that you expect depends on the communication system you are analyzing. In wireless systems and so on, the bit error rates are rather high. But in wired systems like the ones that we will study, we want bit error rates of very low values, okay, so that it runs continuously for years and then there is no error and so on. I mean, it depends again on the particular link, and also we will be looking only at the transceiver part of it. There is also additional stuff. There can be error control coding and so on, which you may study in other courses, where you make raw bit error, you make some errors in decoding, but then that can be corrected later by some redundancy and things like that. Okay, we won't worry about those things. But typically in serial links, the kind of bit error rates that you would see are of the order of 10 to the minus 12 or 10 to the minus 15. Okay. So just to give you some number, Q of 6, that is, if Vp is 6 times the sigma, the error rate is about 10 to the minus 9, and Q of 7 is about 10 to the minus 12, and Q of 8 is about 10 to the minus 15. Okay. So this means that you had 5 millivolts of noise sigma, then you need 40 millivolts of signal amplitude at the input of the slicer to get an error rate of 10 to the minus 15. Okay. If you have 40 millivolts or higher, that is 8 times the sigma, you will have a bit error rate of 10 to the minus 15 or lower. Is this okay? So this appears in various places. So essentially now when we design serial links, right, your transmitter design and maybe even the receiver design will tell you the value of Vp. So you have to choose this, and it may have influence on power dissipation and other things. Similarly, the way you design your circuits will tell you the value of sigma, okay, because I mean you can design more noisy or less noisy circuits. It again has an implication on power dissipation, okay. So as you will see, most likely in analog ICs class, scaling the circuit will decrease the noise variance and increase the power dissipation in the same proportion, okay. We will see that those examples here also. So essentially our job would be to estimate the value of sigma, and this sigma is, remember, this is this calculation is applicable only to Gaussian distribution. Okay, if you had some other kind of distribution, it won't be. But the random noise in circuits does have Gaussian distribution, so this is applicable. So essentially, the basic type of calculation that we need to do are to be able to calculate sigma from the circuit. Okay. So that's why I also gave you the sort of primer about the random processes. It's not an extensive treatment of random process, of course, but it's just good enough to be able to calculate the value of sigma at the end, okay, when you do noise analysis. I think I already mentioned that resistors will have random noise, and similarly MOS transistors will have random noise. So, and that noise is described by its spectral density, okay, and that spectral density, of course, then from the transistor you will have some complicated circuit, you will be taking the output somewhere else. You have to calculate the spectral density, let's say just before you make the decision, okay, and from that spectral density you will have to calculate the variance or sigma. Variance is sigma square, standard deviation is sigma, okay. So that's the kind of calculation that we will do. Is this okay? Fine. So let's try to go in that direction by looking at circuit models and so on. So before that, just a reminder of what I had already mentioned. If you have a random process, again I'll consider zero mean stuff here, and for this type of random noise it's also Gaussian, although we will encounter other distributions in different places. We have multiple instances of the random process, let's say x1, x2, x3 and so on. Okay. We said that basically there are many. So first of all, at every instant you can describe the random process by the probability density function, and for stationary processes it is the same at all times, we said. Okay. And we also wanted an idea of whether the random process is changing rapidly or slowly. To do that, what we said was we will take an instant t and instant t plus tau and multiply the two. Okay. So this is x of t, this is x of t plus tau, right? And take its average over the ensemble. When you say average over the ensemble, you have to weight it with the probability density function, okay, and this is defined as autocorrelation. For stationary process, again it depends only on the difference, the time shift, okay, not this t. For cyclostationary process, it can also depend on t in some periodic way. We don't have to worry about that now. This is okay. So at least intuitively, hopefully you are able to understand why this measures how the random process is varying, that is whether slowly or quickly, right? I told you that if there is essentially it is measuring the correlation of values at t with correlation of values at t plus tau, okay. Again, you may have heard the term correlation at least in a regular context, right? Not in the sense of a mathematical definition, but that's basically what it is, right? It's basically telling you how one thing depends on the other. That's the idea, okay. And essentially, if things don't vary over this time scale, then this product will remain positive and you will end up with a large number, and if it has varied quite a lot and the value here has nothing to do with the value there, you will end up with 0. That's the idea, okay. Where? Yeah, you have to take actually it is I mean maybe I should say it's the joint probability of these two, okay. Maybe I shouldn't write it like this. I'll just say, yeah. So let me say this, okay. Yeah, I think I should probably not have written that. So this is the thing, okay. You take the expectation of this over the ensemble, okay. But we will not be doing this calculation directly, except probably in really trivial cases. So this is okay. So now I also told you that if you let's say take the Fourier transform of each of these things, okay. Now this Fourier transform you have to be little careful. Maybe I shouldn't say Fourier transform. I'll say the power spectral density. I earlier described the difference between spectral density, the energy spectral density that you use for an energy signal versus the power spectral density that you use for a power signal, right? In energy spectral density, the energy spectral density is nothing but the magnitude squared of the Fourier transform, okay? But for signals which have a non-zero average power, this measure diverges. So you take the average power, you have a 1 over t. It looks like the Fourier transform, but you have a 1 over t with t going to infinity. I think, let's see. Where did I have that? So this is the energy spectral density, what you see at the bottom here, and for the power spectral density, you do this. This is the Fourier transform integral, right? If this 1 over square root t wasn't there, basically it would be that. But to get a finite measure, when you have non-zero power, you need this, okay? And then you take this function with t going to infinity. Right? If this part wasn't there, this would be the energy spectral density, right? Because this is there, you will get for a power signal, a finite measure, and you calculate that. Let me just call it Sx1 of f, Sx2 of f, and so on. And you take the, you average this. You will get the same as what is the Fourier transform of the autocorrelation function. Okay. So again, that basically gives you an idea that this, whatever we calculate from this thing doesn't look like your conventional, anything related to your conventional Fourier transform, right? So you take some weird function here and then you take the Fourier transform of that. But it is related to it, okay? Meaning you consider the power spectral density of each of them and then average them, you will end up getting the same as the Fourier transform of this autocorrelation function, okay? Is this fine? So the practical thing that we need to know is the Fourier transform of this, the expectation of x of t, x of t minus tau or t plus tau. This is Rx of tau. And if you take the Fourier transform, you will get a function of frequency which is Sx of f. Okay. Now, most often the way we end up using it is, what is Rx of 0 for 0 time shift? This is basically expectation of x square, okay? And this is again for stationary process, it's not dependent on the time, right? It's only, it's basically, this is the variance. And you know the Fourier transform relationships. So how do you get this from the Fourier transform? It's basically the integral of Sx of f over all frequencies. Okay? Is this fine? So the way we use these concepts is actually rather simple in that we calculate the spectral densities at some point. Let's say in this particular case, when you make the decision, okay, and you integrate that spectral density from over all frequencies, you will get the variance and hence the standard deviation, and that you can use to calculate the bit error rate. Is it okay? So now we will look at essentially the noise of every component will be described usually by the spectral density, and from there you have to be able to calculate spectral densities at other points in the circuit, and that is the regular circuit analysis. Okay. Any questions here? So finally we need to be able to calculate spectral densities at different places if you want to calculate the noise variance there. Okay. Now I think we already discussed this. If you pass a current I through a resistor R, the voltage is supposed to be I times R, but in reality it will have plus some noise voltage. Okay. Or it may be easier to imagine this if you apply some voltage across a resistor R. It's supposed to have a current V by R, and in addition it will have a noise current. This may be easier to imagine in the sense you imagine your slab of material, which is the resistor, and then you take some cross section somewhere. Okay. And what is the current after all? It's the flow of electrons, right? So let's imagine that you can trace the flow of individual electrons across this cross section. Now you know that because the temperature is greater than zero, absolute zero, so you will not have a steady stream of electrons flowing in one direction. Okay. What you will see is electrons like buzzing around crazily, like back and forth. What happens in a resistor is you have fixed atoms in the lattice, electrons will collide and then go back and forth in various ways. This current V by R means that on average the electrons will be flowing in some direction at a certain rate. The current is after all the rate of flow of charge, right? But if you look at the instantaneous current, the electrons will be going back and forth across any cross section. So that's the way to imagine the noise in a resistor. It's quite easy to do that, right? And this is true even if this voltage is zero. That is, even if you don't apply any voltage, on average there won't be any electron flow from one side to the other. But if you look at any cross sections, electrons will be crossing back and forth. Just means that on average they will be going equally in one direction as the other direction. Okay. So this again, I think from physics you probably have an idea that this random motion of electrons increases with increase in temperature. Okay. So this noise current In, this is described by a spectral density. And the spectral density of In, SIN, turns out to be, I'll come to some details of this, but the simplest model that we use, it says that this is constant for all frequencies. Okay, that is, it is the spectral density of a resistor noise is constant for all frequencies, and such a spectral density is known as white spectral density. Okay, this is related to the white color which has all the colors, right? That is all frequencies. So that's why it's called white spectral density. And the value of the spectral density is 2 kT times R. Okay. So the noise, the spectral density of the noise current in a resistor, basically the spectral density of this is 2 kT R over all frequencies. Okay. Now one thing is, I mean, it's actually quite common, and this is how it's usually done, that for real signals you can either use the double-sided spectral density or the single-sided spectral density. Both are used, but in this case conventionally it's the single-sided one that is used. That is, instead of plotting it from minus infinity to infinity, you do it only from 0 to infinity, and that value will be 4 kT times R. Okay, if you plot the single-sided spectral density, it is simply the double of this one, right? Huh? Oh, 4 kT by R, sorry, I think in both places I messed it up. This is the noise spectral density of the current, so this is 2 kT by R, or 2 kT times the conductance, and this is 4 kT divided by R. Okay. So if you use the single-sided spectral density, it is 4 kT by R for frequencies from 0 to infinity. So this is the model that circuit designers commonly use. You end up using the single-sided spectral density. Now both have their conveniences, this double-sided and single-sided, but this is what we use. Okay? Is this fine? Now, what is the variance of this? What is the variance of this noise? Infinite, because if you integrate this from 0 to infinity, you get infinity. Now that doesn't make any sense, but of course this is also an approximation. So this, I won't go into this 4 kT by R, this kT, it turns out it's not kT actually. This again you would have learned from some basic physics, and you may remember terms like this ultraviolet catastrophe and so on, from which you got this quantization of energy levels, all that stuff. But this, instead of this kT, essentially what you have is sorry, what is this? You can go and read up about this. I won't go into this. This H is the Planck's constant, and nu is the frequency. Now if you look at this function, this actually goes down with frequency because of this exponential, right? If frequency goes to infinity, it does go to 0, unlike this kT itself, which is independent of frequency. But you also see that if you use an approximation where h nu is much less than kT, okay, so then the denominator, the exponential, becomes approximately 1 plus h nu by kT, and the 1 goes away and you will get k times t. Okay. So this expression is approximately kT when this condition is satisfied. So what is the frequencies for which this is valid? Can you quickly calculate it? Do you remember the value of Planck's constant? Yeah, some 6.6 times 10 to the minus 34. So and you can assume room temperature, that is 10 power 11. Okay. How much is it? 10 to the 12. Okay. So 10 power 13. Okay. Yeah, it's around that. So by the way, this kT, the K is Boltzmann's constant. How much is that? 1.38 times 10 to the minus 23 what? Joule per Kelvin. And T for room temperature, we take it to be 300 Kelvin. So if you calculate this product, it comes out to be close to 4 times 10 to the minus 21 joules. Okay, it's worthwhile remembering this because we always get K times T together. We don't use the Boltzmann's constant by itself, right? So KT is 4 times 10 to the minus 21 joules. So this nu is 4 times 10 to the minus 21 divided by H, which is 6.6 times 10 to the minus 34, okay, which again comes out to be roughly 6 times 10 to the 12, so 6 terahertz, right? Now this frequency, basically it says that for frequencies much less than 6 terahertz, this approximation is valid. So physically, of course, the spectral density does go down to 0 at very high frequencies, okay. But on the other hand, for our calculations we don't have to worry about it, because all our frequencies, even at the highest bandwidth that we make, which is probably of the order of 100 gigahertz, it is still like much smaller than this. Okay, so it is safe to assume h nu much less than kT and go with this white noise assumption. The only issue with the white noise assumption is this contradiction that you get where the noise variance is infinite, but we know that it's not. So as long as we are calculating for bandwidths much smaller than this, it's okay. Is this fine? So we'll continue with this white noise assumption. Now similarly, if you plot the voltage noise spectral density of the resistor, it will be 4 kTr. Again, if it's the single sided spectral density, or 2 kTr if it is the double sided spectral density. Is this okay? Fine. What will be the units of the noise current spectral density? So the easiest way to see, if you don't already know, is that the integral of SIN is the variance of the noise current, okay, ampere square. So SIN itself will have units of ampere square per hertz, and similarly SVN, the integral of this has voltage variance of the noise voltage, or volt square. So this has units of volt square per hertz. Okay. Now in engineering literature, sometimes you will see essentially this 4 kTr. So let's do it for room temperature for a 1 kilo ohm resistor. What will be the value of 4 kTr? (16) 10 to the minus how much? 18. 18 volt square per hertz. Okay. Now sometimes it's because this volt square is an unfamiliar unit, and we use volts, voltages and currents, right? So volts and amperes are more familiar. So this thing can be written as basically 4 times 10 to the minus 9 square, with the units also inside. Sorry, not square root of volts. Volts per square root of hertz square, right? So this kind of units you will see, this is 4 nanovolt per root hertz. Again, when you do many calculations, this is worthwhile remembering. The noise spectral density of a 1 kilo ohm resistor is 4 nanovolts per square root of hertz. Okay. So it means exactly the same thing. To the actual spectral density is the square of this. Okay. Is this fine? And similarly, if you calculate the same thing for the noise current density for a 1 kilo ohm resistor, what would you get? You would basically get 4 picoampere per square root of hertz square. Okay. These are some really elementary calculations. Now the way you model this is, as I said, the way you model this, not only for a resistor, for essentially for anything, right? So you can, so it says that basically you have IR which comes out from Ohm's law. So I'll put a star here now, but I won't be doing it later. So this is a noiseless resistor. If you had a noiseless resistor, you would get I times R, and then you have a voltage source on top of that. Okay. So this has a spectral density of 4 kDr. Similarly, if you want to use this model, you have a noiseless resistor of value R and you have a current IN whose spectral density is 4 kT divided by R. Okay. So you model these noise in components as additional current source or a voltage source. For most components you can use either one, and while doing analysis sometimes it's convenient to use current source and sometimes it's convenient to use the voltage source. Okay. And also you are already familiar with this type of equivalence, right? If you had, forget that it had anything to do with noise, you have Vn and R and you have In and R. Okay. At these terminals, these are equivalent to each other, right? I mean, what is this? Thevenin and Norton equivalent, that's all. So this is the Thevenin equivalent and this is the Norton equivalent of the same thing. So what is the relationship between In and Vn? Vn is In times R. Okay. Now, so now let's say In is some random variable and this is a scaling factor, okay, or a random process. So if you know the spectral density of In, what will be the spectral density of Vn? Times R square. Okay. So because this comes from something related to the variance which has the square. Similarly, if this was some random variable, the variance of Vn would be variance of In times R square, or the standard deviation of Vn would be simply be standard deviation of In times R and so on. Okay. The autocorrelation of Vn would be autocorrelation of In times what? Again R squared. Okay. So when you scale something, essentially the variance gets multiplied by square of the scaling factor. Variance, spectral density, autocorrelation, everything. Okay, these are all again very simple, but I am just going through it as a review. Any questions here? So from this also it obviously makes sense that Vn is the spectral density of Vn is 4 kT times R, which is the spectral density of In times R square. Okay. Is it fine? Now let's say I put two resistors together, okay, and together in series. So I'll have Vn1 and Vn2. Okay. What is the spectral density of Vn1? 4 kTr, or in fact let me make this R1 and R2. This is 4 kT times R1. Spectral density of Vn2 is 4 kT times R2. Okay. And obviously this can be represented as a single resistor R1 plus R2, and this is Vn1 plus Vn2. Okay. What is the spectral density of this? Four kT? Yeah. Why do you get that? So actually, when you sum two random variables, well, let's calculate the variance. I mean, let's say you have x1 and x2, and to calculate the variance, again, I'll assume zero mean here. So this will be E of x1 square plus expectation of x2 square, plus you also have 2 times expectation of x1, x2. Okay. So this is the variance of x1, this is the variance of x2, and this, what is this called? This is a correlation between x1 and x2. Now if they are correlated, then you will have this additional term. If the two random variables are uncorrelated, then this part will become 0. Okay, expectation of x1 times x2 will become 0. So they will be uncorrelated, and you will simply add the variance. If you add two random variables, the variance of the sum is the sum of variances. Okay, and if it holds for variances, it also holds for autocorrelation as well as power spectral density. Okay, so you simply add power spectral density. In this case, Vn1 and Vn2 come from two physically different resistors, and they are definitely uncorrelated. And this is true of all the random noise. Random noise generated from physically different components, they are uncorrelated. Okay. So generally, we don't have to deal with correlated random noise. There may be some exceptions, but generally we don't have to do that, because essentially we will have noise from many different components, and we have to find finally the combined contribution of all these things. Okay. So when you add them, there won't be any correlation between them. So you can find the spectral density due to each of those components, and finally you add them together. Okay. This is okay. And this anyway makes sense also, because if you thought of this as a single resistor, the noise spectral density had to come out to be 4 kT times R1 plus R2. This will happen only if the noise is uncorrelated between these two parts. Okay. So a noise from different resistors, but not only different resistors, different MOS transistors, etc. are uncorrelated. Okay. Is this fine? The what slide? Yeah. Okay. Now the resistor's voltage noise spectral density is 4 kTr. Okay. What is the autocorrelation function? They are related how? How are these two related? Fourier transform. The Fourier transform of autocorrelation is the spectral density. So what is the autocorrelation? Impulse. What impulse? What is inside the delta? What is the argument of delta? Tau. Okay, what is multiplying the delta? 2 kTr, 4 kTr, what is it? So you have to be careful with the single-sided spectral density. So if the two-sided stuff is 2 kTr, so this will be 2 kTr times delta of tau. Okay. So Now, so this says that with this model, I mean, I already told you that this 2 kTr being constant for all frequencies is only an approximation. In reality, it does go down with frequencies. So, at very high frequencies. But assuming this model to be true, so this says that basically noise is correlated only at that, with only noise at that time instant. Okay, if you go to any other time instant, it is uncorrelated with that. Okay, this is fine. So if you take, let's say you take resistor noise samples at different instances, they will also all be uncorrelated from each other. Okay, that's basically what this is saying. Now, these are essentially basic definitions and the resistor's noise model. Have you seen all of these in some course? In which one? Huh? IC design. Okay. I guess not all of you have done IC design, right? How many of you have not seen any of this? The noise of resistors and all these things? You have not seen it. Okay. You will be doing it. Yeah, I think many of you are in that situation. Anyway, let's go through these calculations. So now, let's start working out noise in simple circuits. We just looked at a single component, the resistor, but let's look at this. This is a first order RC low pass filter. Okay. Now I want to calculate the noise at the output due to the noise of the resistor. So how would I go about doing this? What should I do? So first I have to calculate the transfer function. Okay. Then what do I do with that? Yeah, so basically the power spectral density, so this noise times the transfer function is the output noise. So the power spectral density at the output will be the power spectral density of Vn times the magnitude square of this transfer function. Okay. So of course, this is a function of frequency, this also will be a function of frequency. And integrating this from 0 to infinity, we will assume that we are using single-sided spectral densities, will give us the variance of the output noise. Okay. So please do it for this circuit please do it offline, and then we can discuss that in tomorrow's class. Okay. Again, this is most likely a result that you already know, but go through the calculations and we'll discuss it further.